Okay, good morning, everyone. Let's wrap up node voltage analysis today, and then we'll move on to mesh current analysis. So again, the homework for node voltage was set for Saturday. I will there's just a couple more things to go over, and then I will move that back to like Sunday. And then I will introduce mesh current analysis today. So students will be expected to actually open up the mesh current analysis homework, just at least take a look at it. You might want to get started with the extra credit tutorials if you wish. And one note or one point about extra credit problems. If you recall at the beginning when I went over the syllabus, I mentioned this is a multimodal and multi-level class or multi-level course. The levels, well, it's for the homework assignments where I have practice problems and tutorials that is somewhat beyond the scope of the normal syllabus. So sometimes some students are interested into going deeper into this, into the topic, learn a bit more things that are outside the syllabus. And so that is the purpose of those practice problems and the tutorials and the video solutions. So this was a comment that I received in the, in one of the feedback forms. And it said that this has not been covered in class. And so I'm just addressing. I have no idea which section the student belongs in. So I'm just addressing to all students. Those extra credit problems on the homework, they are for students who wish to go beyond. Again, any student can take those because those extra credit points count towards everything, towards your final grade. So again, you might encounter from time to time, you might encounter certain topics in there which are not within the normal scope of the class. And, so it's a little bit of extra work, hence the extra credit. Okay. All right. So having said that, let's get to our problem here. So we talked about how we obtain negative voltages for VA and VB when a reference is VC. All that simply means is that the levels for A and B, well, below sea level, they're underwater. But if you choose A as reference, then VA would be 0 volts. I hadn't written it down. I don't know if I covered this, but I hadn't written it down. So that's what I'm doing here. So VA would be 0 volts. What would be VC in that case? Remember, voltage is just the difference in potential between 2 points. Whether this is 0 or whether this is 0 does not change the fact that the distance between the two remains the same. So if your analysis is correct and you choose A as your reference, VC would be exactly the same magnitude, which would be plus 13.5. And VB in that case would be about what, minus 39, approximately minus 39 volts. Your answers would be the same. The value for VB would change, but only because my reference node is different. So students could choose any node as a reference. They could choose any current direction. I would look at that reference node and I would look at your values and see if they match up or not. Yes. So not for the purposes of that analysis, no. So then it would just be, whatever you would say it's VD, right? So you would solve and the value for VD would be different because that point is being measured with reference to a different point. As an example, students go work in a lab, right? So if they're working in a lab number 3 use dual power supplies, positive and negative. So if you have, let's say if this is 0 and this is, so if this is ground and this is minus 15, actually, let's do it here so students online can also look at it. So if 0 volts ground is, let's say, as you said in the example, is VD, and this is minus 15 volts, you take your multimeter and you put the positive reference here and the negative reference here. What would you measure? Minus 15. Oh, yes, positive 15, because, wait, I'm confusing myself. This is 0 and this is minus, so it's below. So you would obtain positive 15. Yeah. If you switch it around, you would say minus 15. So it's all to do with the reference node. Even in this example, if you choose B as your reference, then VB is 0 volts and VA and VC would be correspondingly different. Both would be positive numbers because the level would not change. This level would remain the same. So if B is 0, then VC would be plus 52.9 volts. So again, students can choose whichever node they want as a reference. They can choose whatever current direction they wish to assign to a particular resistor. If your analysis and calculations are correct, you will end up with the right answer. Even if the values, as I just showed here, that number, the magnitude might also be different. But that doesn't change the fact that the distance between all 3 points remains the same. All right. Okay, so one final point about solving circuits with voltage sources in there is applying a super node concept. So if you have a voltage source in there and you're trying to solve it using node voltage analysis, how would you write the expression for the current flowing through that voltage source? It's impossible. With this technique, it's impossible, right? Because a resistor current I can describe using Ohm's law. It simply be IR1 is equal to VR1 divided by R1. But if I have a voltage source and I call this IS, how would I write, or how would I describe IS? I cannot describe it at all. So the concept of super node was created, and it's kind of like a shortcut. We simply take the power supply out and short it out. So my circuit would become something like this. And I have now combined all of this into one single junction. Again, there is a wire going from the top all the way to the bottom. So it's one single node, it's one single junction. And we call that as the concept of super node. We simply remove that voltage source because we cannot describe an expression for the current flowing through that voltage source. Remember, we use Kirchhoff's current law, KCL, right? We use KCL to write out our equations. So if we cannot describe the current source, the current to the source, then we cannot write a KCL expression. So we make it a super node. Yes. Node is a junction. Junction of two or more components is a node. Anytime you have two or more components connected together, the wires that connect those, that's a node, electrical junction. That node in a circuit schematic on a circuit diagram can be a short dot, can be a short wire, a short line, or could be a very long line. but it's all a node. So as an example, again, your power outlet has 3 prongs. You take a extension cable, like a 100-foot extension cable, like the orange ones, plug it into a wall, you would still expect to receive power, electrical power, 100 feet away. That entire wire, that is a node. Well, it's 3 different wires, so 3 different nodes, but the point stands that it's the entire wire is still the same electrical junction, so it's still the same node. Yes. Mm-hmm. So there is a derivation that goes along with it. We typically don't do it for non-EE classes, just in the interest of saving time. And again, it's not within the scope of the syllabus, but I went over this in the other class because we were having lots of discussions. I can quickly show you how and why. So this is R1, R3. Again, this is not something that you have to learn, so you don't have to write it down if you don't want to. R2, R4, and the rest do not matter. So hypothetically speaking, let me assign a current to here as IS. Okay. Now, IR1, IR2, IR4, and I'm going to say this is IR2. Okay. So our job is to apply KCL to generate equations. With a voltage source, I cannot. So it's an unknown variable, and I cannot have that unknown variable in my equation because I cannot solve it. So the only way to do that is to eliminate that variable. And supernode allows us to eliminate that IS variable directly. Otherwise, I would have to do all of these steps. So I would write an expression, KCL, let's say here at X and Y. I would have KCL at X, I would have IR1 plus IR2 equals IS. 2 currents entering a junction, 1 current leaving. So simple KCL expression at one end, and then I apply KCL at Y at the bottom node. I have IR4 plus IS equals IR2. IR4 entering Y, IS also entering Y, and then IR2 is leaving the junction. Make sense, right? Simple KCL equation. Now, if A equals Z and B equals Z, I can write A equals B. So rearrange this term, this equation in terms of IS, and I equate both of these, eliminate IS. So here I can say IS equals IR2 minus IR4. And from both of these two, I can write IR1 plus IR2 equals, oh, sorry, not IR2. What was this? This is IR3. IR3 equals IR2 minus IR4. I take IR4 on the other side, I get IR1 plus IR3 minus plus IR4 equals IR2. If you look at the super node, IR1, IR3, IR4, and IR2. If you apply a KCL expression here at this node, after you short out that voltage source, so you remove it, you have the exact same equation. You have IR1 plus IR3 plus IR full, all coming into the junction, equals IR2, which is what we obtain right here. Yes. So that we don't have to do all of this work. Efficiency. Just for the purpose of writing that one equation. That's it. As I said, the derivation is here. From this derivation, we come up with the concept of supernode. And as I said, just so that we don't have to do this. I mean, as engineers in your own field, you would have come across systems and problems which have multiple solutions, right? You as an engineer is tasked with the, with determining the most efficient and least time-consuming method. And so that's simply the case here. It's the same thing as the voltage division and current division. Voltage division and current division are derived directly from Ohm's law. If you apply the principle directly, it allows you to skip 1 or 2 steps. And so here it allows you to skip about 3 or 4 steps. And that's the concept of the supernode. If you're not comfortable with that concept, it's fine. You can go ahead and do that. I'm not going to specifically ask you to show me the concept of supernode, okay? All I care about is if you're able to apply the method correctly, and if you're able to derive the, or not derive, determine the values for that problem. And that's it. But does this make sense? Right? Supernode is, again, just derived from just applying KCL at both ends of that voltage source. Simply allows us to skip a few steps. There is also an additional relationship you can write. So in this case, let's say this is node 1, node 2, node 3, and the bottom one is node 4. If I choose 4 as my reference, I automatically have an answer for V3, which is minus 15 volts, right? Minus 15 volts. But I do have V1 and I do have V2. I cannot write an expression for the current through here, so I would apply a supernode. Or you can just write KCL at both ends and then eliminate a few more steps, which is fine. An additional relationship can be defined between V1 and V2 because I know the value of the difference in potential, 10 volts. This is plus. V2 is connected to the positive end of the voltage source, so it's higher than V1. So I can write V2 minus V1 is equal to 10 volts. I can describe each one of these variables in terms of the other. So I can write V2 is equal to V1 plus 10, or V1 is equal to V2 minus 10. So that eliminates one more variable. When I write my KCL equations and I describe each resistor voltage in terms of these node voltages, I have 2 unknowns, V1, V2. And because I can describe either one using these 2 equations, I can eliminate one more. If I choose this first one, I would only have V1 in my equations. Wherever V2 appears, I would plug in V1 plus 10, or I could describe it in terms of V2. Either way, it does not really matter. So it's an advantage to have multiple voltage sources in the circuit because I now only have one unknown variable. V4 is 0, V3 is minus 15. V1 and V2 can be described using here. I only need one equation because I have one unknown variable. Let's take a 10-second pause while you think over that statement. The circuit seems complicated at first, but it's actually very easy. Does everyone see how 4 unknown variables or 4 nodes goes down to 1? Let's write it out. If 4 is reference, then V4 is 0 volts, and therefore V3 is minus 15 volts. And I can take the other voltage source, and let's say I choose to describe everything in terms of V1, then I can say V2 is equal to V1 plus 10. So no matter how many equations I write, V1. So all equations will only have one unknown variable, which is V1. So I only actually need one equation. Does that make sense? Right? Well, we write KCL expression. When we actually write the KCL equations, then we'd have V2 in there, we'll have V1 in there, we have V3 in there. Well, V3 already you know the answer, minus 15. And wherever we have V2, we would plug in this. So V2 is now described in terms of V1. So only need one equation. You can apply that at either node 1 or node 2. And you'd have your answer. All right, let's take that question further. If you look at the left side, node 1, if you apply KCL at node 1, again, remember, this is node voltage analysis. We apply KCL to generate our equations. So if you apply KCL at node 1, and I chose, let's see, I chose, just to stay consistent, I chose R2, IR2 going like this. I chose IR1 going like this. And this would be IS. All right. So node 1 and 2 are combined together. I would have R1, R3, and C. R3, 2 and 4, R2 and R4. So I eliminated the 10 volt source. When you eliminate it, it's only for that one step, not for the entire problem. That's the thing that confuses students. We are only eliminating it just to write that one equation. That's it. Once we write that equation, that voltage source is back in there. The rest of the analysis. So if I want to write my KCL, this is now all one single node. That's the super node. I have IR1 going this way, IR2 going this way, IR3 going here, and IR4 was, what did I say? IR4 was coming down. So IR4 was coming down. So at that super node, KCL at the super node gives me IR2 is entering, and then all three are leaving, which is R1 plus IR3 plus IR4. We actually receive the exact same equation even when we applied it at the bottom node. So IR2 is equal to IR1 plus IR3 plus IR4. IR2 VR2 divided by R2, VR1 divided by R1 plus VR3 divided by R3 plus VR4 divided by R4. And from this point on, you simply plug in the values for those resistor voltages in terms of those node voltages. Again, node 4 is a reference in this example, and then you just solve it from there as normal. You'd have V1, V2, V3, V4, plug in the values, and you'd find your equations. Yes, V1 is the voltage at node 1. VR1 is the voltage across resistor R1. Hence the different subscripts. These are resistor voltages. Again, node voltage analysis. You write the KCL expression first, express each current in terms of the resistor voltages using Ohm's law, and then you express each resistor voltage in terms of the node voltages. Clear to everyone? Any questions? It's just node right here. So it's right here. So this is V1 here. This is V2 here. We eliminated that with a short. Now all we are doing is we are applying Ohm's law, and we obtain VR1, VR2, VR3, VR4. VR2 in this case would be the voltage across resistor R2. I can write that as V1. This would be V1 minus V4 divided by R2. VR1 is V1 minus V3 divided by R1. VR3 is V2 minus V3 divided by R3, and VR4 is V2 minus V4 divided by R4. V4 is equal to 0 volts. V2 you can plug in as V1, what is it? V1 plus 10. Yeah, V1 plus 10. And then V3 is minus 15 volts. The only thing left in that equation, or the only unknown variable left in that equation, is V1. Solve for V1, you have the node voltage at V1. Once you have the node voltage at V1, add 10 to it, you have the node voltage at V2. And then, find all the other resistor voltages and all the other resistor currents. Does that make sense? Right. The steps do not change. steps remain the same. Again, as I said, whether you apply supernode concept or not, you will end up with the same equations. The supernode concept allows us to find the answer in one step, or like in one equation. Right. Okay. Well, mesh current analysis. So node voltage analysis, we applied Kirchhoff's current law. Mesh current analysis, we will apply Kirchhoff's voltage law to generate our equations. Okay. Now, mesh current analysis is a little bit confusing. The reason is the mesh currents are purely hypothetical. They're theoretical. They do not exist in real life. Okay. First thing is we identify a mesh. Mesh is easy. It's a simple electrical loop that does not have any other loop inside it. So if you look at this circuit, we can identify 3 electrical loops right away. I'm going to call this M1, M2, and M3, right? Mesh 1, 2, and 3. I can identify an electrical loop here and here. 1, 2, and 3. Right? How many total loops in the circuit? Remember, electrical loop is basically you start at a node or a junction point at one point in the circuit. You go around the circuit and you come back to that exact same point by multiple different pathways. Each unique pathway is an electrical loop. So our brains can automatically see we have 3 loops right there. But there are multiple ways to come back to that same point. So let's count. 3 at first. 4. 4 is a combination of 1 plus 3. 5 is a combination of 3 and 2. You have 6, which is a combination of 1 and 2. Sorry. And then there is 7. 7 is a combination of 1 plus 2 plus 3. You can start at any point in the circuit and you can come back to that same point. So if I start at the bottom left corner, I can go around the circuit this way and come back. I can start here and come back. Right? I can start here, go this way, come back to the same point. I can start here and come back to that same point. So any closed pathway is an electrical loop. Yes. 7 is the outer loop. So that's 7. Oh, I didn't know you can do that. That's 7. So it's 1 plus 2 plus, actually, 3 plus 1 plus 2. Okay. But you don't have to worry about electrical loops for this technique. You only have to think about mesh. Again, a mesh is a simple loop. Okay, it's an electrical loop that does not contain any other loop inside it. So if you look at 4, 5, 6, and 7, 4, 5, 6, and 7 all have other loops inside it. Right? 4 has 1 and 3, 5 has 3 and 2, 1 and 2, and 1, 2, and 3. So it has multiple loops inside it. So they are not meshes. So 4, 5, 6, 7 are not meshes. But 1, 2, and 3 are individual small loops. So they are each a mesh. Again, as I said, our brains can automatically identify meshes because it's a closed pathway. And so we can easily identify meshes. So for the purposes of this analysis, we don't have to think too much. Identify the mesh and assign a mesh current to each single mesh. You can choose a clockwise direction or you can choose a counterclockwise direction. Either ways, it does not matter. My default is always a clockwise direction. I always choose clockwise. But similar to node voltage, once you make an assumption at the beginning of your problem, you stick with that assumption until the end. You do not change those assumptions halfway through your solutions. Okay, otherwise you'll end up with the wrong answer. So again, I have M1, I1, M2, I2, M3, I3, all of them going in the clockwise direction. So in this case, since I'm applying KVL, I'm summing up voltages. By the way, that's my shortcut for voltages or acronym VTG, voltage. Summing voltages, and again, KVL, we learned in chapter 1, right? And you learned in physics 3, you might have learned it before also. You can apply KVL however you want to. Okay, I showed how I applied it in class. If that does not work for you, you're feel free to choose your own. That's absolutely fine. So what do I see? I have for M1, R2, R3, R2. And then I1 going to that mesh. But here's the important point. Mesh currents are purely hypothetical. They are purely theoretical. They do not exist in real life. We make an assumption and we use this only for the purposes of analysis and for solving the circuit variables. And so, even though we do not consider the other meshes, we do have to consider the mesh currents. Okay. So if I was to write a KVL expression here, I would say 3 voltages VA, VR2, and VR3 equals 0, right? 3 voltages, voltage source, resistor R2, resistor R3. But before we do that, we have to assign polarity to the voltages according to the direction of the mesh current. So mesh current I1 going through R2 causes a voltage drop. Which end is positive, left or right? Passive reference configuration. Current always goes from high to low. High is noted as plus, this is noted as minus. So if current is entering through the left, where is my plus sign? On the left. So I1 causes a voltage drop in this direction. How about R3? Plus at the top or the bottom? So I1 is entering through the top. So plus, minus. And then we have to account for the other mesh currents, meaning I2 and I3. And this is only because a resistor is sharing a mesh. Okay, we are only working with mesh 1 here. We're writing an equation for mesh 1, but we still have to account for I2 and I3. In the previous section, I was teaching this and I forgot I3. And so my answer would be incorrect until a student pointed it out. This is a shared branch. You have to account for all the mesh currents. So I would have I3 entering from the right. So that would be plus. This would be minus. And I2 enters R3 from the bottom. So that's plus. And this is minus. And that reinforces the point that the mesh currents are purely theoretical. They do not exist in real life. You cannot have two voltage drops between the same 2 points, especially in the opposite direction. You cannot have two currents flowing in the opposite direction. You cannot have two currents, period. Remember, current flows because there is a difference in electric potential between 2 points. If both points are exactly the same, whether they are 50 volts or 0 volts or 100 volts does not matter. If they are both at the exact same potential, it's steady until one of the points goes up. If this point goes up, current is going to go from, well, your left to right. And if this point goes up, then it goes from right to left. So physically, it's impossible to have a current flow going in opposite directions. So again, I1, I2, and I3 are purely hypothetical. They do not exist in real life. It's only for the purposes of analysis. Okay, but we still have to account for those in the equations. So my equations actually would be VA, and I'm going to write plus VR2 minus VR2 plus VR3 and minus VR3 equal to 0. This plus for VR2 and this minus for VR2 is a result of my assumption of the direction of the mesh current. If my I3 was going in the opposite direction, my voltage drop would be plus on the left, minus on the right. Then I would have plus VR2 plus VR2. Important point to note, okay? In node voltage analysis, we assume a direction for the branch current through a resistor. When we make that assumption, automatically we assign a polarity. Point of entry would be plus, point of exit would be minus. It's the same thing here. We assume a direction for I1, I2, and I3. So in both these cases, the currents are going in the opposite direction. The reason we would obtain the correct answer at the end is because even if my current direction was reversed, when I account for mesh 3, I would have the opposite value. So instead of having positive variables, I would have negative. My equations would balance out. I would end up with the right answer. It's similar to choosing a reference node. Remember in that example, in node voltage analysis, whether you choose A, B, or C as your reference, your answer will always be correct. It's the same concept here. You can choose whichever direction you want for your mesh currents, but in the end, your equations will all turn out to be correct. Well, as long as you don't make any errors, your answers will also be correct. So again, I1 causes a voltage drop plus to minus from left to right. IR3 causes a voltage drop going from minus on the left, plus on the right. And for R3, I2 causes a voltage drop going plus at the bottom and minus at the top. If my chosen directions for I2 and I3 were reversed, if they were both counterclockwise, all of these voltages would be positive. But my equations would still be correct. Okay. So when I look at those problems, that's how I would grade them. So then I would take these, I would apply Ohm's law and express each resistor voltage in terms of the mesh, in terms of the mesh current. Okay. So you apply Ohm's law. This is from KVL. Then you apply Ohm's law. And I would obtain VA plus VR2 would be I1 times R2 minus VR2 would give me minus I3 times R2 plus I1 times R3 minus I2 times R3 equals 0. Because of the chosen direction of the current, because they're opposite, you can simply combine it and write it as VA equals, actually, you know what, let's not skip steps, plus R2, I1 minus I3 plus R3, I1 minus I2 equals 0. Some students like to skip the Ohm's law step and go directly to the final line. Again, you can do so if you want, but again, you better be sure that what you're doing, that you know what you're doing and have confidence in yourself. I typically never skip steps like these. Sometimes I do, depends on the circuit. Again, first step is to write the equation from KVL, then apply Ohm's law, substitute each voltage in terms of the resistor, mesh current, and then just plug in those values and you have your equation in the form of AX plus BY plus CZ is equal to A, is equal to whatever constant. Algebraic equations. Once you have enough number of equations to solve for your variables, you can find the value for those mesh currents. Once you find the values for the mesh currents, you can find any resistor voltage in the circuit. Same concept as node voltage analysis, except this time we choose mesh current analysis. Okay, 10-second pause. Think over it. Let me know if you have any questions. Yes. Sure. That's not a mesh. That's an electrical loop. These are all loops. Mesh is a simple loop. Does not contain any other loop inside it. Okay. Again, as I said, we don't need to identify a loop. We need to identify a mesh. So we sum up voltage. Yes. So we would apply. So this is not over yet. So we would apply for M2. So this is for mesh 1. Yes. Yep. And then similar to the concept of supernode, we also have super mesh. It's written by the Avengers. Okay. If you have any questions, I'm around. We'll end class here today. We'll pick up here again on Monday. As usual, there will be a quiz on Monday. Node voltage analysis is the topic. I will post the announcement on Canvas as I did last week. I pretty much do it every week. I think the first quiz one, I sent an email versus an announcement. But again, remind me, when I post an announcement on Canvas, it comes to your email also, right? Okay, so please make sure that you look at those. So quiz on Monday, node voltage analysis. The homework will be pushed back from Saturday to Sunday. And then mesh current has been introduced. So please open up that homework, take a look at it. And then I hope to finish up measurement analysis. Well, Monday is the quiz, so probably Wednesday. So the homework for mesh current, consider it to be assigned. The due date would be sometime next Thursday or so, I would say, or maybe Friday. Don't know yet. Depends on how fast we cover it. Okay. All right. Have a good weekend, and I will see you all on Monday. Yes. Yeah. It's hold on.